Hello everyone, I'm Sudarshana from EE21. In this video, I'm presenting my seminar on the formulation of discrete wavelet transform. This seminar is a part of the course EE5004. The talk is mainly classified in 6 topics. We start with the origin of the wavelet transform, and then we analyze the drawbacks of the already existing transform that led to a new transform. Then the wavelet theory and the role of a very important mathematician Ingrid Dauberkis, the discrete wavelet transform and its impact. We also discuss about its mathematical aspects and also the later advancements in the field. A set of seismic signals are given here. These were observed in the Mount Rainier volcano by scientists of the Pacific Northwest Seismic Network of the University of Washington. From here we see that different phenomena like an earthquake or a landslide or a glacier slide or an avalanche has its own unique seismic signal. In late 1970s, Jean Morley was trying to analyze such seismic signals. He was using the conventional tools like the windowed Fourier analysis, but at that time he found that such conventional tools often created numerical artifacts. Numerical artifacts here can be considered similar to a mathematical error. So Jean Morley, in order to overcome this, along with Alex Grossman, developed a continuous wavelet transform, the CWT. The core idea behind their work was a wavelet. So a wavelet, according to them, was a simple oscillatory function of finite duration. They modeled their seismic signals by combining the translations and dilations of this simple wavelet. And another important real-life signal is a human speech signal. Human speech signal, from the table given here, we find that the 26 alphabets of English has a wide range of frequencies in them. Say, the vowels have a slightly lower frequency range from 250 to 2000 Hz, whereas voiced consonants like B, D, and M have a higher frequency range from 250 Hz to 4000 Hz, whereas unvoiced consonants have a much higher frequency range from 2000 to 8000 Hz. So, an example is given here. The speech signal when a person pronounces the word reports. From here we find that at the occurrence of the letter S, there is a higher frequency component, whereas at other letters, say E or an O, the frequency is lesser. So, when conventional Fourier analysis is used to analyze such signal and find the frequency components present in it, we could find that a higher frequency, say 6000 Hz, occurred in the signal, but we won't be able to say exactly where that 6000 Hz occurred. Say, example, the 6000 Hz correspond to the letter S. We won't be able to find where did the letter S occur. Was it at the beginning of the word or at the end of the word? So, this Fourier analysis was losing all the information about the time localization, and also the human speech signals has significant transient components which the Fourier analysis wasn't able to analyze effectively. So, the limitations of discrete time Fourier transform. One of the limitations we just saw was that it loses the time localization of the frequency component. So, we need a new transform which has temporal resolution, that it should be able to analyze both the frequency component along with the time of occurrence of it. The discrete time Fourier transform was uneconomical at times. Say, there was a momentary impulse. The discrete time Fourier transform even now has to do a lot of computations over the entire signal to find the frequency components present. So we need a new transform that can localize its search. The discrete time Fourier transform is basically trying to fit the sinusoidal signals into the given signal. So we just use the sine and cosine basis in the discrete time Fourier transform. But we need a new transform that allows us to use other bases. The windowed Fourier transform can be said that it uses time localization, but there was an issue here also. The windowed Fourier transform uses a rigid time frequency window. So the frequency window cannot be varied as per our wish. So this was a drawback, and the time complexity was also higher. The discrete time Fourier transform had a time complexity of the order of n squared, whereas the fast Fourier transform, the later variation of it, had time complexity of the order n log n. So we need a new transform which can perform operations with a much lower time complexity, say the order of n. So what is a wavelet? Before we understand the wavelet transforms, we'll understand what a wavelet means. The formal definition of a wavelet is that a wavelet is a waveform of effectively limited duration that has an average value of 0 and a non-zero norm. An example of a wavelet is given here. From here we see that most of the energy of the wavelet is concentrated between the time intervals of minus 2.5 and 2.5. That is a span of 5 seconds. So the most of the energy, almost 99%, gets concentrated in just these in just the interval of 5 seconds. And also it has been found that this Morley wavelet given here has an average value of 0. This is the formal part of wavelets. But now, what is a wavelet? Put in simple terms. A wavelet can be thought of as a magnifying lens that lets you spotlight the information that matters to you the most. Say, we watch a cricket match. There could be artifacts in the grass because we don't care much about the grass present. But say in cases where we are looking for a close run out or a LBW, in that case we are concerned about the accuracy of the image. So in that cases the wavelet comes in rescue. So the first known wavelet basis. In 1909, Alfred Haar, a Hungarian mathematician, proposed a Haar sequence. The Haar sequence is an orthonormal system for a space of square integrable functions in the interval 0 and 1. This is till date the simplest possible wavelet. This Haar wavelet can be seen that it has discontinuities at 3 points at 0, 0.5 and 1 because the wavelet has a value of 1 from 0 and 0.5 and the value of minus 1 from 0.5 and 1. So this Haar's wavelet is discontinuous, so it is indifferentiable also. But this Haar's wavelet is useful in analyzing signals which has sudden transitions, because there we make use of this disadvantage post of the non-differentiability. Now, what is an orthogonal or orthonormal wavelet? A wavelet whose associated wavelet transform is orthogonal is said orthogonal wavelet. Now, an orthonormal wavelet is an orthogonal wavelet normalized to magnitude 1. So, an orthogonal wavelet is a wavelet whose inverse wavelet transform is adjoint of the wavelet transform. For a long time, many researchers believed that the Haas wavelet was the only possible orthogonal wavelet. But this was disproved in 1985 by Wismayer, a French mathematician who constructed the second orthogonal wavelet. He called it the Meyer wavelet. The later revolution in the field was of the multi-resolution analysis. The multi-resolution analysis was proposed by Wismayer and Stephen Mallet, both French mathematicians, in 1988. So, multi-resolution analysis was breaking the signal into different components and then add the different components together and then extract the original signal. This was useful because signals often contain many meaningful components, but our interest lies in only certain subset of these components. So in these cases, the multi-resolution analysis proved useful because it allows us to narrow our analysis. The method of decomposition was important for the data analysis, and this MRA is mainly characterized by the scaling function used. So, Ingrid Daubechies, a mathematician, first reviewed this MRA and also the other algorithms present in vision decomposition and reconstruction to establish her own orthonormal basis of compactly supported wavelets. In this, she created a compact support wavelet from a finite length sequence. which can also be extended to higher dimensions. Now, who's this Daubechies? Daubechies was born in 1954 in Belgium. She did her undergraduate physics in the Free University of Brussels and later her doctorate in theoretical physics from the University of Brussels. Daubechies generally had a great love for the powers of two. It's evident because she also celebrated her 64th birthday instead of any other. Her best discovery was at the age of 33 when she developed the continuous wavelets based on quadrature mirror filter technology. She published her work on the orthonormal basis of wavelets, which she called the Daubechies wavelets, in 1988. This work brought her many honors, from a honorary degree from Harvard to a MacArthur Fellowship, a National Academy of Sciences award in mathematics. She was the first woman to receive this award, and she was also the first women professor of the University of Princeton. Daubechies has applied her mathematical skills in many fields like restoring fine art works. For example, the Ghent altarpiece. It's a 15th century piece of art termed the first known oil painting. This Ghent altarpiece has in itself 12 different images which all correspond to a church scene. This analysis of the Ghent altarpiece was hard because there were 12 images, and when people tried to do X-ray analysis of this, they were not sure of which part of the image gave the results. So Daubechies and her team are working on restoring the fine art piece. And Daubechies is also someone who believes that research is for everyone with interest. There have been accounts of her from her own students saying that how Daubechies has impacted their work and their interest towards research. So what was a wavelet according to Daubechies? According to Daubechies, wavelet is a mathematical caricature. A caricature is the general cartoon we see every day, wherein the important or the notable characteristic of a person is represented as a cartoon character. Similarly, wavelets, according to Daubechies, is also a mathematical caricature because it lets you know the most important trait of a signal. This wavelet is similar to how our human eyes function. Human eyes generally focus in more detail at a focal point and leaves the rest of the view a little blurry. In 2012, Daubechies was honored with the title of Baroness by the Kingdom of Belgium. At that time, she wrote the line "Divide ut comprimas," that is, divide so you can compress, in her motto of coat of arms. This was taken from a similar line, "Divide ut regnis," which was said by Julius Caesar. It means divide and rule. So Daubechies, in honor of her work on wavelets, modified this line and wrote as "Divide ut comprimas" on her as a motto of the coat of arms. So, Daubechies created a family of orthogonal wavelets called the Daubechies wavelets. These are the defining points of the discrete wavelet transform today. This set of Daubechies wavelets is characterized by the maximal number of vanishing moments for a given support. This can be considered similar to the number of roots of a polynomial. These Daubechies wavelets are the building block for wavelet analysis, and these are in constant use in the mathematical tools present. Example, Mathematica allows you to directly use the Daubechies wavelets in it, and MATLAB also allows a basic implementation of the Daubechies wavelet. Daubechies also wrote a book called the 10 Lectures on Wavelets, including all her work and analysis of the wavelets. This earned her the American Mathematical Society Steele Prize for Exposition in 1994. Now, discrete wavelet transform. So from the animation given here, we find that there's a single wavelet which has been expanded and contracted, and it's shifted in time to find how much of that particular variation is present in the signal. This can, when put in mathematical terms is given here, the mathematical expressions of the continuous wavelet transform and the discrete wavelet transform. From here we see that S is the scale parameter and tau is the time shift factor. So S defines how much the wavelet is compressed or expanded, and tau here is how much the wavelet is shifted in time, and here psi is the basis wavelet or the mother wavelet. So in the continuous wavelet transform, there are a lot of wavelet coefficients generated because we are calculating wavelet coefficients for every possible scale. So in order to overcome this, we choose S and tau, the scale parameter and the time shift factor, to be discrete so that it doesn't generate huge amounts of data. This led to the discrete wavelet transform. It was found that if S and tau are chosen as multiples of 2, the analysis was more efficient and accurate. Here, the variable A is similar to the time shift factor and the variable B is similar to the scale parameter, and we are restricting our analysis to P distinct time instance, and this is the mathematical expression for the discrete wavelet transform. So now the impacts of the discrete wavelet transform. The early applications of the discrete wavelet transform was in the fingerprint database of FBI, which will be discussed in detail soon. Then the animation of films like A Bug's Life. So what are the current trends in the discrete wavelet transform? The current buzz of artificial intelligence can also be boosted by using a wavelet analysis. Say for example, the generic example of differentiating the image of a cat from a dog. We can feed in images of the cat and dogs by extracting only the essential information into it. Say, we know that there's a difference between the appearance of a cat's eye and a dog's eye. We can just use wavelet analysis to extract the useful information and then feed it into the computer. By this, we can analyze the difference with a lesser number of images, and it's also done with higher accuracy. So artificial intelligence can be boosted because the computer needs only lesser number of data, lesser amounts of data, and the analysis can also be efficient. Now, the discrete wavelet transform is also useful in denoising signals like the electrocardiogram. Now, coming to the FBI's fingerprint database, it's estimated that around 50 million fingerprints are stored at the FBI. Currently, FBI is using WSQ, the wavelet scalar quantization, to compress the fingerprint data it has, and later it began using the JPEG 2000. So now we'll analyze the difference between using the regular JPEG and the WSQ. So fingerprint is a unique feature for every human. So it's a reliable source of personal identification, and its uniqueness is getting exploited for many security and identification purposes. The real-time method of fingerprint identification is generally done based on optics. So as there's a large chunk of data getting stored, the images get compressed to fit in our data size, and by this we should also not compromise on the image quality. So FBI and the UK Home Office Police Research Group conducted tests analyzing the performance of JPEG, which was using discrete cosine transforms. By this it was found that the JPEG method produced many tiling artifacts at edges, and it gave a higher error for higher compression ratios, and it was not robust for compression errors. So, in order to improve the performance, FBI began using WSQ. This WSQ has a superior preservation of fine scale details. It uses symmetric extension methods for boundaries. When looked closely, fingerprints have different features of symmetry, and the wavelet method of analysis was also proving efficient at boundaries, whereas JPEG used to produce a lot of artifacts at boundaries. WSQ was resistant to it, and this also gives the user the control over compression. The WSQ was superior in all aspects, and it can also be seen from the images given here that for the same compression rate, the clarity of the JPEG image is lesser than the clarity of the WSQ image. Now, what is WSQ? WSQ is a lossy compression. This preserves high resolution details and can let us achieve higher compression ratios. One another important aspect was that the WSQ was invariant to rotation. Say the wave or say a fingerprint was slightly tilted, but even then the WSQ method was able to extract proper information from it and analyze it properly. Now, what is JPEG? JPEG is the most common image format which we generally use every day. Digital cameras and other photographic image capture devices also use this JPEG. The images which we see on the World Wide Web and the images which we share on chatting devices every day are also based on JPEG. So, what is JPEG? JPEG is the Joint Photographic Experts Group. It is a group among International Organization for Standardization, the International Electrotechnical Commission, and the International Telecommunication Union. The latest advancement done by JPEG is that they developed the JPEG 2000 in 1997 to 2000, in the period of 1997 to 2000. This was a discrete wavelet transform based method. This has improved compression performance and it has multi-resolution decomposition. It lets the user customize their own signal noise ratio and resolution. And this JPEG 2000 didn't produce any blocking artifacts in comparison with the previous JPEG. But despite the advantage of the JPEG 2000, it's not widely used. It's because the JPEG 2000 is not supported by web browsers today except Safari. But JPEG 2000 is continuously used in places where high resolution of the image is needed. Example, the digital archives, the discussed database of the FBI, the satellite imaging, medical imaging, and biometrics. JPEG 2000 has been used in that, but it is yet to get implemented in the web browsers today. So, the discrete wavelet transform is a time shifting operation. So, this was not shift invariant. This flaw led to the shift invariant fast wavelet transform, which was developed by Stephen Mallet in 1989. It's called the fast wavelet transform. So, from our discussion, we have seen that there have been many different signal analysis methods, starting from the Fourier transform, wavelet transform, and then now the fast wavelet transform, and many more to go. Signals today are so wide ranged and so rich that a single method of analysis is not sufficient, that a single method of analysis that can be applied for every possible signal is totally imaginary. It was said so by Wismeyer, who says that it's hardly an exaggeration to say that we'll introduce almost as many analysis algorithms as there are signals, because the signals today are so rich and complex that a single analysis method cannot serve them all. This is the brief timeline which we discussed today. We started with The work of Morley and Grossman, their first form of wavelet analysis. Then we discuss about the multi-resolution analysis of Maya and Malay. Next, the Darbouquet's wavelets. And we ended with the fast wavelet transform proposed by Stefan Mallet. So here we have a set of images of people whose work has been tremendously supporting the signal processing and image processing today. We start with Fourier, Joseph Fourier. He was analyzing heat patterns, and then he developed the famous Fourier transforms. And we have John Tukey and James Cooley, both developed the modern fast Fourier transform, reducing the time complexity of Joseph Fourier's Fourier transform. Next, we have Wismaya and Stephen Mallet, who worked on MRA, and Stephen Mallet again worked on fast wavelet transforms. Darbouquet, who laid the foundation of the wavelet analysis today. And the most recent person who's working on the field is Terence Tao. He's working on he's a mathematician and a child prodigy who is working on compressed sensing. This has been useful in many signal processing applications today. So mathematics today has evolved from being studying about the geometry of shapes to geometry of forces. Today, mathematics has evolved to be about geometry of information. It has been evident from the notable work of all these mathematicians. Mathematics gave the foundation of the signal processing and image processing we see today. Engineering has just been using these mathematical tools to apply in areas of interest. So, ending in words of Darbouquet, which she said in her famous conference talk, math can help as always. Thank you.